something, you overestimate how much people know about your subject. So if at any point I talk about something as if it's widely known and it is not, please stop me and tell me. On the other end of the spectrum, this first part of the talk is going to be relatively hand-wavy. So for the specialists in the room, yes, I am aware that I'm not being precise. You can fill your own blanks. You know enough about the subject. I just didn't want to get into the nitty-gritty of the definitions. So, a new model of DG categories, that is the title of my talk. So we will be talking about DG categories. Now in my abstract, I promised that I would give some kind of introduction to DG categories beforehand. And that is going to be this first part. So this introductory section is going to be divided into a series of parts. So first, we're going to motivate DG categories by talking about something a little more concrete, which is the derived category on a ring. Then we will talk about localizations for a little bit and use that to introduce DG categories. We will do an extremely brief detour on model categories, and then we will end with some things that are, well, we're not satisfied with what we did before, so where do we go from here? So let's start with what a derived category is. So for the entirety of this talk, both the introductory and the technical part, we fix K to be a commutative ring. And we're going to define a complex of modules to be a diagram of this form. So all the AIs are modules over a ring, and then we get morphisms from one module to the next, such that the composition of two of them is 0. In other words, we have that the kernel of the next one is in the image, is contained in the image of the last one. And we will denote that category of complexes by CK. Now, if you know what a category is, the first thing you're going to be saying is you haven't defined a category. You've defined the objects of the category. So what are the morphisms on this? Well, morphisms will be things of this form. So we have, for every module, we'll have a morphism that goes from a degree I on one to degree I on the other. And we will ask that this commutes, so that this composition is equal to this composition. And of course, the most important thing to remember is that as much as it looks like it, this is not a ladder. Now, if we're going to talk about derived categories, one of the most important things for this will be the cohomology of a complex. So if we have a complex, where's the pointer? If we have a complex on a ring, for all z's, we can define the I cohomology of A to be an object a model, which is the quotient of the kernel by the image. Now, because we defined the differential as we did, this is well defined. And if we have a morphism of complexes, this cohomology induces a morphism on modules of this form. And the idea is that in algebraic geometry, a lot of the time, we want to see cohomology is a very good invariant. So we want to see what we can do on the level of a cohomology. So we say that a morphism of complexes is a quasi-equivalences of complexes if for all the integers the induced cohomology morphism is an isomorphism. And we will want to study morphisms of complexes up to quasi-equivalence. And that is going to be our derived category. So we define the derived category over a ring, we denote it by dk, to be the category of complexes up to quasi-equivalence. This is not really super precise, but I will give a more precise definition later. And now this is just to give you a sense of how useful this thing is. This is just a very quick search on arXiv of papers with derived category in the title. So I'm pretty sure all of these articles are from the last month or so. So derived categories are important and they are thriving. So how do we define this more precisely? So our goal is going to be constructing a category in which the complexes of modules are the objects and the quasi-equivalences are our isomorphisms. How do we do that? Well, our first option will be the Gabriel-Sysmans localization. So this is relatively intuitive as an idea. The objects of dk, if we choose this, are the same as in the category of complexes. And for the morphisms, we will take zigzags of this form. So we have the morphisms that go from left to right are just morphisms of complexes. And then we accept the idea of having morphisms going in the other direction, which are the quasi-equivalences. So we're formally inverting those quasi-equivalences. Now, in honor of Arne, I have said up to a certain equivalence relation, because he wants me to tell whenever I'm lying to you. So this is pretty nice. It is intuitive. It is a good classical localization. So it would be really nice if this was the right concept for us, right? Now, in the immortal words of Mick Jagger, we can't always get what we want. So this is not what we want to be our derived category. Why not? Well, the Gabriel-Sysmans localization has the correct universal property. If we have a functor from complexes to n, such that the image of a quasi-equivalence is an isomorphism, then it exists a unique factorization through this Gabriel-Sysmans localization. So technically, it does do what we want it to do, but it doesn't do it well. So first of all, this localization has size issues. Because we're adding all these formal inverses, we can and we usually do end up in a higher universe. So we're getting something that's very, very, very big. Also, the category of complexes has limits and co-limits, while this version of the derived category doesn't. So we're losing quite a bit of machinery. And also, probably most importantly, for people doing algebraic geometry, classical algebraic geometry invariants, like the K-theory, Horsey cohomology, cyclic cohomology, don't work as well as we would like them to in this context. So we are in a situation where can we find a localization that works better than this? And that is where dg-categories come in. So let me define what those dg-categories are. So if we have T a dg-category, we define D a dg-category to be a category enriched over chain complexes. What does that mean? It means that we have a set of objects, and then for every two objects, we have a complex of modules instead of a set. We're adding some structure to our morphisms. And then the composition morphism will then be given by the tensor product instead of the Cartesian product. And the unimorphism is given by this dg category that's just 1 point and k as the complex concentrated in degree 0, plus associativity and unit conditions that I'm not going to get into. And of course, if we have a category, we need to see how the morphisms are. So if we have two dg categories, a dg functor is given by a morphism of sets on the objects, and then for every two objects, a morphism of complexes, plus associativity and unity conditions, etc., etc. So the category of dg categories and dg functors is going to be denoted by dg-cat. That is our basic definition. So is this definition clear for everyone? This is good?
What is a small f is?
Here?
Yes.
Oh, it's just a digifunctor f is given by this. So
That's the name of the functor is f.
yeah, the functor is f. I just forgot to write it.
Okay.
In this case, f could be the map between the sets, right?
Yeah. So we can have an example. So one of the first dg categories is actually the category of complexes itself. How do we give a dg category structure to this category of complexes? Well, the objects are the same. We have the same set of objects, and for every two complexes of modules, we're going to take the product of the morphisms from aj to bj plus I. And for the differential, we will get this formula. Now, this might not look the formula is not very clear. So let me give you an example of what this means. So this is the module in degree 1. What we do is that we get the morphisms from bi to ai plus 1. And the differential, what it is doing is it's doing this composition on one hand and this composition on the other hand. So the differential gives us a morphism that is queued one level more. So what we are looking at is knot ladders that are more and more skewed. Okay? And of course, we can get back our usual category by taking the morphisms to be the cocycles on degree 0 of the morphisms in this category. So, last thing I'm going to say about constructions of dg categories is if we have a dg category, we can define the homotopy category of T. We denote it by these brackets to be a category whose objects are the same and whose morphisms are the cohomology in degree 0. So again, we're taking a dg category and we're getting a normal category in the exchange. And so our goal here because we said that we were doing all of this because we wanted something that would give us the derived category that worked better. And the thing that we're going to do is we're going to construct a dg category whose homotopy category is the derived category that we had at first. Okay, so we're doing a kind of a dg enhancement situation. And how do we do that? So if T is a dg category, we define a T-dg module to be a dg functor from T to the dg category of chain complexes. So we've given chain complexes structure to be a dg category. So this is just a functor in the dg category. In other words, on a more concrete level, it means that for every object in T, we have a complex in the complexes, and for every two objects in T, we have a morphism of this form. Okay, and we will denote the category of T-dg modules by T mod. And now we're going to take a small detour on model categories. Now, I'm not going to explain precisely what a model category is, because that would take us another good 10 minutes, and it's a very formal definition. So this is even more hand-wavy than the rest of my talk until this point. We say that a category has a model structure if it comes with an initial and a final object and three classes of morphisms: weak equivalences, fibrations, and cofibrations that satisfy some conditions.
So you mean you have a category and you add additional information to it by saying certain of the morphisms I call weak equivalences and certain other ones I call fibrations?
Exactly, yes. This, usually the process of proving that something has a model structure is finding what are the right fibrations and what are the right cofibrations to make all these conditions I'm not telling you work. So yeah, that is exactly what we're doing. Why are we doing that? Because first of all, if we have an object in a model category, we say that it is fibrant if the morphism from the object to the final object is a fibration. And we say that an object is cofibrant if the morphism from the initial object to X is a cofibration. So we have found two classes of objects that are special in a way. And the idea for all of this is that if we have a model category, the localization, the Gabriel-Sisman one, the one we saw before, by the weak equivalences, not of the entire category, but only of the objects that are both fibrant and cofibrant, is actually the correct localization and has no size issues. So as we said before, that the usual localization has this, gets very big. We don't have that in this case. And we call that localization the homotopy category of M. And we will denote it by HO of M. Okay? So finally, for all dg category T, the category of dg modules is a model category. We have such a structure. And then we have this equivalence of categories. That the homotopy category, in terms of DG categories, of the fibrant cofibrant objects on TDG modules is equivalent to the homotopy category, the localization of TDG modules.
Something the
Yes.
original, the CK, with the DG structure is not a model category. What phase?
Complexes are a model category.
And what is
So-
an initial and a final objective in complexes?
The zero complex is the initial object, and I think it's K. I think it's also the terminal object. So yeah, so yes, just zero.
What is L? Sorry, I forgot.
We haven't defined it. It's L is the fibrant cofibrant TDG models. So this is just a definition. Probably should have put two points there. So the idea is we found a category whose homotopy category is a localization of something. So we did not get what we wanted. We tried, and we got what we needed. Just yeah.
So is there some T for which T mod is your original category of complexes?
Yeah, that is exactly it. But thank you. It was a very good question. Means that my talk is understandable. So exactly, if we have K a commutative ring, we can define a DG category which has just one point and K as its endomorphisms. We call it a BK. So a BK DG module is just a complex of modules over K. If you're not convinced by this sentence, you can write it down. It is basically by definition. And in particular, that means that the homotopy category of the fibrant cofibrant objects on BK DG modules is our original derived category. So we have found a DG enrichment of derived categories of this form. And we won. We solved the problems that we had in the beginning. This is the right localization in the DG categorical context. So on the level of DG categories, we have the properties that we expect a localization to have. This has no size issues. It has limits and co-limits. And it behaves correctly with the classic invariants. So we got everything we wanted, right? Well, in the immortal words of Mick Jagger, we can get no satisfaction. Which means that the moment we solve one problem, we find another one. This is good, but is it perfect? Yes.
So what is the category that now behaves better for the classical invariant?
What is the category? Why is the category that behaves better?
I don't know, maybe then I'm confused. I thought like one of the problems we solve is that we have created something that behaves correctly with classical invariants.
Yes.
This is the derived category.
Yes, this is the derived category.
The better one should be speaking much of the homotopy category. The enhancement should be the better one.
Yes.
So you have more because if you take a homotopy category with enhancements, you can derive it. And then, yeah, more
Mhm.
It's the,
Yeah, so because we have given it more structure, the problems that we had in the original category are solved in this context.
So, or does it mean that we actually did not have any problems?
Yeah, I mean, that's
Because
I
think,
the
like,
category as
so
well.
we're always have an enhancement.
yes, but for example, I don't know, like, so this decay is the decay that has the universal property. So I'm a bit confused. Like, you want something with a universal property that is unique. So
Yes.
the problem was with the construction.
The problem is with the construction in a way. Like size issues, we can just do the model category thing.
Yeah, for example.
In this case, so I will be completely honest with you. This is stuff that I haven't worked with in a while, so I can give you the reference if you want to like check on the details. But for the things work better, it's just that because we have more structure, decay still has those problems, but we can work in here.
So that's the one, for example, that has limits and volumes.
Yeah.
Okay. So, yeah, perfect.
Yes.
It sort of has everything in there, but I think practically to really compute things or something.
Yeah.
Yeah. So yeah, it is a very good question.
And this taking homotopy process
Uh-huh.
induces a dg structure on the resulting thing, or not?
Like
the decay.
This.
Yeah.
This decay is still a category. The homotopy actually takes out the dg structure. So we have an enhancement, it is this one, and what I'm saying is that if you get like the submerged, that is not the right word. Like the category that lives in it. Underlying, thank you. If you take the underlying category, you get the classical derived category, which means that we haven't gotten very far.
What goes wrong if you do the same that you did with complexes, but in the derived category? So you have a morphism of complexes in the derived category is a morphism up to quasi-isomorphism, right?
Yes.
So you can also twist it as much as you want and do the product over set.
Mm-hmm.
And consider that. Like, why go something has to go wrong there?
So you're suggesting instead of doing this,
Just a question. You grab your category of complexes and you give it a natural dg structure, right? By looking at maps of complexes. Okay.
Yes.
Maps of objects in decay are maps of complexes up to quasi-isomorphism.
Yeah. So give the dg enhancement to decay directly. At the very least, that is going to give you even more size issues, I think. Because if your decay is already too big, let me see. I think the limits and co-limits might not work if you do that. But I am not sure. The thing is, this is a way more general construction.
I think isn't that exactly what a dg enhancement of the derived category is?
Do you think if we actually peel down this definition, we're going to end up with the exact same thing?
Yeah, it sounds like if you want to create the houses into dg modules, you're creating a dg enhancement of the category, right?
Yeah, maybe. Again, this is a way more general result. This, I am hand waving, this entire thing works with any abelian category, not just modules over a ring. So I wouldn't be surprised if this case just like dissolves into nothing when you start writing it out. I would have to write it down, honestly. If you're curious, we can like try and write it down at the break. It's I'll admit it's been a while, so I don't have all the details in mind. But yeah. So what does go wrong once we have all of this? What is the next thing that makes us want to go, okay, but can we make it even better? Well, DG categories have a tensor product. We have modules have a tensor product. So we can define a tensor product like this, in which the objects of the tensor product are just the Cartesian product. And for all two objects in the product, we do the tensor product on the complexes of morphisms plus compatibility conditions. And we get to the situation where this category of DG categories has a model structure, has a monoidal structure, and the two of them are not compatible. So what does that mean? It means that if you take two cofibrant objects and you do the tensor product, the result might not be cofibrant. So there's something there that is not playing correctly. So our new goal will be to find a new version of DG categories where it would be easier to define a good monoidal structure. And that will be the goal of the second part of this talk. So if I have managed to make you interested, please come back after the break. Otherwise, well, thank you very much for coming anyway and listening to what I have to say. And if you want to learn more about any of the things that I've told about, these are some classical references that I've used for my talk. So the whole idea of DG categories as localizations comes from Bertrand Toen's lectures on DG categories. So all the details of what I hand-waved are in there. Amnon Diakutieli, I hope I'm not butchering their name. Introduction to Derived Categories is a good introduction to derived categories as in the context of algebraic geometry. And of course, if you want to learn something about model categories, Mark Hobby's book is the basic entry point for anyone wanting to learn about them. And I cannot recommend it enough. And that will be all for this section of my talk. So in this first part, we've talked quite a bit about localizations and localizations issues and how do we solve them and that kind of thing. So I'm going to start with a tiny bit of history. So one of the classical ways to solve problems with localizations in general is model categories that we very briefly mentioned before. So model categories were introduced in 1967 by Quinen, and they are really useful and they're really practical, and Violeta really likes them, apparently. But as had been said before, they also have a lot of structure. And it's also all structure that we lose the moment we do the localization. So it's a lot of work to just lose it at the end. So over the years, there have been other propositions on how to treat with this problem. So we have in 1980, Dwyer and Kahn introduced simplicial localizations, which are a certain type of simplicial categories. But simplicial categories have the same issue that we mentioned with dg categories, which is that they have a monoidal structure and a modal structure, but the two of them are not compatible. So we need other things. And that has fueled people over the years. So we have in 73, Bormann and Vogt introduced quasi-categories. In 89, Dwyer, Kahn, and Smith introduced Segal categories. And then all the way in 2001, Rezk introduces complete Segal spaces. And we'll have to wait all the way until 2007 for Berner on one hand and Dwyer and Tierney on the other to give all these things model structures and prove that they are all Quillen equivalent, which basically means that they are all models of the same thing. That is the thing that we usually call infinity categories. So we have all these models of the same thing. And we can do something, we can see something similar happening with dg categories. So if infinity categories are old, dg categories are even older. So we can see them being used already in the 60s. But we will have to wait all the way until 2005 for Taboada to construct a model structure on them. And we see that this model structure is not compatible with the monoidal structure, which will push people to find other models for dg categories, a little bit in the same way as they did with infinity categories, trying to use infinity categories as a as an inspiration. So we have Kohn proves in 2013 that dg categories are equivalent as quasi-categories to k-linear quasi-categories. The thing is, I think anyone who has worked with k-linear quasi-categories will agree with me that they are not the most user-friendly setting.
What are k-linear quasi-categories? Because I thought there was an issue there.
Huh?
I don't know what you define as k-linear quasi. What is Kohn defines k-linear quasi?
In the very sense which means an infinity category with some action.
The stable stuff. I know.
Yeah, stable k-linear in infinity categories, yeah, in the sense of Lurie.
Okay.
But yeah, so that is the other problem, is that in order to get to the definition of that, you have to get through, what, 2,000 pages of higher topos theory plus 600 pages of higher algebra.
Hmm.
If you're just trying to do geometry, it's probably not something you're willing to do. So it is not the most user-friendly model.
Good. Can I something? So is there a reasonable brief definition of what a quasi-category is?
It's a simplicial set such that, help me here if I say something that's wrong. You have these horns, thank you, which the idea is that you take out a side of the largest degree. And the idea is that you can fill in, no, how's the diagram?
The other way around.
The other way around? Yeah, that way, yeah.
Yeah.
So the idea is basically that you can fill all the horns. So it comes down to you have a composition up to some higher level thing. Does that make sense?
So you have objects and you have morphisms, but the composition is a bit of.
The composition is up to 2 morphisms.
Okay.
And the composition of 2 morphisms is up to 3 morphisms. And yeah.
But what do you?
Yeah, so explain the answer.
I'm feeling too comfortable.
Yeah. They're not my favorite models, so. What?
I'm just sitting right there.
Sorry, there's a reason I don't do quasi-category. So we have this proof that DG categories are equivalent in the sense of quasi-categories to k-linear quasi-categories. And then in an article in 2020, Packard defines dg-Segal categories. And last year in his thesis, Mertens defined a DG quasi-category. So we have to say, I'm saying that these are all models of DG categories, but I probably should be saying they're all models, because there are no proofs yet that any of these are equivalent. And in fact, none of them, except for usual DG categories, have a model structure on them yet. And in every one of these cases, it's work in progress. So we can't prove that they're equivalent as model categories because they're not model categories yet. But if you have been following this historical introduction, you will notice that I have given 1 DG version of simplicial categories, 2 DG versions of quasi-categories, and a DG version of Segal categories, but I have given no DG version of complete Segal spaces. And that hole here is where my work is. I'm going to try and find a DG version of complete Segal spaces. Now, apart from the joy of filling a blank space, why would we want to do that? Well, complete Segal spaces have some advantages to them. On one hand, it is easy to get a model structure on them, or at least it's easier than it is in other cases. And also, it is constructed in a way that is, to quote Daniel Dagger, a kind of presentation by generators and relations. We'll give a smaller number of generators, and we will say, and they have to have these conditions. And that is, in particular, a really easy way to do things with morphisms. So in particular, that might give us a way to tackle the question of what are the automorphisms of DG categories. There's a paper by Toen from 2001 calculating the automorphisms of infinity categories. And he does it using the classical complete Segal spaces. So we could probably do something similar in this case. So once I have convinced you that this is worth doing, let's do it. So this talk will be divided into 4 sections. We will start with some prerequisites of things we need to know in order to follow the rest of the talk. Then I will define dg-Segal spaces and complete dg-Segal spaces and get a few results in. Then I will give a very sketchy proof of why this thing is a model for DG categories. And then I will end with some perspectives, some work in progress, some things that we're doing at the moment. So let's start with some prerequisites. So usually I start this by giving the definition of a DG category, but thanks to the way this is organized, I don't need to. So let's start directly with what the model structure of this thing is. So we have a morphism in DG categories. We say that it is quasi-equivalent if we have this. Now, you don't have all the information. Oh, yes, you do have, because we saw it in the last part. We say that it is a quasi-equivalence if the induced morphism on the homotopy category is essentially surjective. And if for all two objects, the induced morphism on the complexes is a weak equivalence in the complexes. And Taboada proved in 2005 that the category of DG categories admits a model structure whose weak equivalences are these quasi-equivalences. And for the people in the know, that is a covalently generated model category, which means basically that is a model category that is relatively well behaved. Now, I'm going to talk about something that I'm going to be using for the rest of the talk. So we denote by GR of CX, of CK, the category of directed graphs enriched over cochain complexes. So apparently in this group, you usually call them quivers. Yeah. So it's the same thing. And for the people who don't work with quivers, that means it's a directed graph in which the edges are cochain complexes instead of just edges. And we have equivalent junction between graphs and DG categories. And we will define a DG category to be free if it is the image of some graph. So we denote the full subcategory of free DG categories by L. And then the other thing is if we have a graph, we say that G is a graph of finite type if it has a finite number of vertices and the edges between two vertices are always perfect complexes. Now, if you don't know what a perfect complex is, you don't need the definition for this. The thing that you need to know is that the category of complexes is accessible, which means that perfect complexes are its compact objects. We can write every complex as the colimit of perfect complexes. Okay, so that is all you need to keep in mind. So we say that a DG category is free of finite type if it is free and the graph it comes from is of finite type.
Sorry, perfect means bounded. So there are finally many that are not zero. The rest are zero.
It is. Yeah, it's quasi
okay.
Up to. Okay. It's bounded and the modules are perfect, if I remember correctly. Projected.
How they finite presentation?
Also,
you know. Yeah. Thank you. Okay. So basically, they're pretty finite. If we. And the last thing we're going to do in this prerequisite section is introducing Dagger's universal model category. So please do not be scared by the block of text. Everything we need to remember is that if we have any category and a model category, there exists a closed model category of this form, so that's functors from C up to simplicial sets, such that we have a equivalent adjunction of this form. Okay? And in particular, we will have to remember, I don't know if you can see it, if it's, is that same, so this direction is just map from blank to the object. Okay, so that is all we're going to need in terms of prerequisites. So what is our goal here? So we're going to try and find a dg version of complete Segal spaces. Complete Segal spaces form this adjunction, so from infinity categories and functors from delta up to simplicial sets. So how are we going to do a dg version of this? We're going to say construct an equivalent adjunction between dg categories and simplicial functors from this thing to simplicial sets.
Sorry, can you go back?
Please tell me this definition is correct.
It's not a definition, but so,
Well, I mean, yeah, it's not a definition.
but so the infinity cut, you mean the complete Segal spaces? There's an adjunction where on the left you have complete Segal spaces. I don't understand what you mean by this sentence.
Okay, so I was trying to make a slide that looked good with the next one. The idea is that if we say that complete Segal spaces are a model for infinity categories, is that we have a equivalent adjunction between complete Segal spaces and other models of infinity categories. Okay. I just didn't want to get into more detail on that. So complete Segal spaces are things that live in here.
Yeah, okay.
That's what I meant. Yeah. But it is not very clear from the. Well, so in this case, we have dg categories, and if we want to find another model, we need equivalent adjunction between dg categories and thing in which complete dg-Segal spaces live. So let's try and construct that. First of all, what is this thing in red? So first of all, we denote the full subcategory of cofibrant free dg categories of finite type by CL. Now, every single free dg category I work with is cofibrant and of finite type. So I will drop cofibrant and I will possibly drop of finite type at some point, just add them back in. All my free dg categories are cofibrant and of finite type at all points. And we get the set of quasi-equivalences on dg categories. If we construct the simplicial localization with respect to the quasi-equivalences. So we define the simplicial CL, the full simplicial subcategory of this localization. This okay? Look very confused.
Is that easier because all your objects are cofibrant here? Is it easy to describe explicitly this simplicial CL because your objects are already cofibrant, or that won't help much?
It makes some construction later easier to make. It's mostly a question of ease for calculation.
After you expect free objects to be cofibrant, it's for dg categories that stuff.
That is not true all the time, no. Yeah.
Yeah, so it's not lifted from the category of graphs and model searches. It's already.
I don't think so, no. Okay. So we have this CLS, let's construct this adjunction. So the adjunction comes from this graph. So let me walk you through it. So we have, no, if I do it with my hands, then people on the Zoom, on the video call cannot see me. So the G star is the morphism induced by the inclusion. L star is the morphism induced by the localization. And these are RE and SING are the morphisms induced by Dogger's model, universal model construction. So you might be wondering, why don't we just put them side by side and compose them? The reason is that while these are all Quillen adjunctions, they don't all go in the same direction, which means that they can't be composed as such. L goes in the wrong direction. So what we do is that we see that SING can be factorized through this thing. So we avoid L Schrick altogether, which means that our adjunction will just be going straight up in one direction and doing this in that direction. But for the purposes of this talk, you can basically see SING as being maps from blank to T, and that should get you through the presentation with no problem. So,
Question?
yeah.
So in the Dogger construction, we have the model category and the category. I assume, so in this case, we only have model category. So is there any model category that's taking the role of just a category, or?
Yeah, in this case, it is pretty much the trivial case is the category and the model category are both dg categories.
The category of categories.
Yes.
Yeah.
So it is just a way, it's just a fun way of getting this functor and this equivalent, this adjunction.
Yeah, so the model structure on this funny dg-cat up is the one induced by Dogger's result.
Yeah, which is basically the classical projective model structure.
Okay. Yeah.
So now that we have the adjunction, next step is, okay, what is the image by this functor SING? So we get our first definition, which is dg-Segal spaces. So if we have a functor in this category, we say that f satisfies the dg-Segal conditions if it satisfies one, that the image of a coproduct is a product, so it commutes with finite coproducts, that the image of the initial object is a point, and then we have this condition. It's a little bit more complicated, and you don't have all the data you need in order to understand it yet. So let me explain that. So if we have a graph, and we have two objects in the graph, and a co-cycle in degree n, we define the graph G not alpha to be a graph of complexes with the same objects as G for every edge different than xy. We don't change anything. And in xy, there's an extra G in there that shouldn't be. We take the complex in xy and we add a beta whose image is alpha. So we're basically killing this alpha in the homomorphic category. And we can see that that construction also as this push forward, where Kn is the graph with two objects and a complex concentrated in degree n, where it's just k. And KCN is the graph with two objects and the morphism concentrated in degree n and n minus 1. So that also gives us the right plane. And so our last condition on the dg-Segal spaces is basically that the image of that push forward is a homomorphic pullback. Okay?
The second condition that's also it's not isomorph, it's like weakly equivalent. Or...
Yeah, it's weakly equivalent.
Okay.
Everything's weakly equivalent. To quote Arne, we're all homomorphic theorists, so everything is a weak equivalence. But so, first things, I said that in this context, it is easier to find a model structure. And here you go. Once we have the right definition, this is a very straightforward proof that we have a simplicial closed model structure whose fibrant objects are the dg-Segal spaces. And we call such a model structure the dg-Segal model structure. So this is just a left Bausfield localization. So very easy, hard to get. But if you are familiar with Rezk's paper on complete Segal spaces, you will know that Segal spaces are not enough to be a model for infinity categories. There is one class of morphisms that should be invertible but isn't. And so the way that Rezk goes about it is by defining something a little more refined, which is complete Segal spaces. So you won't be surprised to know that in this case we have some kind of a similar issue. We have something that should be invertible but isn't. So we're going to define complete dg-Segal spaces. And we're going to do it via classical scenario. So there is a close relationship between Segal spaces and complete Segal and dg-Segal spaces. We have a morphism called the linearization of delta that for every n in delta gives us a dg category with n+1 objects, and just the morphism in degree 0, the complex in degree 0, where it's k in between each one. And that defines a Quinn adjunction between functors on delta up to sets and our functor category. And we call this one the linearization morphism. And we can prove that if we have a dg-Segal space, its delinearization is a Segal space in the classical sense. Which is nice. That means we haven't strayed too far. So we're going to define a complete dg-Segal space by saying that it is a dg-Segal space whose delinearization is a complete Segal space. Okay. Thank you for coming. And we have everything we wanted, because we can see that every object in the image of our functor thing is a complete dg-Segal space. And also, again, the model structure is not that hard to get from here. If we have a simplicial closed model structure whose fibrant objects are the complete dg-Segal spaces, and we will call that the complete dg-Segal model structure.
Is this another localization?
This is also a left boss localization, yes.
From the project.
This is a localization of the dg-Segal model structure localization. But I mean, you can do it in
double localization.
Yeah, you're localizing the localization.
Okay.
I mean, you could perfectly do it in one step, just localize by the 4 things at once.
Okay.
It's just we already have one, so might as well.
And you localize at what?
Ah?
You localize at what?
You mean what is the class of? Do you have my thesis? It's the morphisms from the linearization of. The idea is when you do this localization in the complete Segal model structure, you're localizing by a morphisms of this form. I don't remember what was here. Does someone remember that?
Just like you want the points.
Yeah.
So like the working isomorphism to the
Yeah, I think that's it. So you're just doing the linearization of this in some sense,
Okay,
or you're doing something along those lines. I can't remember exactly.
Okay. I can see later.
It's like, Arne, do you have my manuscript?
No, we can see later.
Yeah.
Why upstairs?
Uh,
I've seen it upstairs.
Yeah, it is upstairs. We have it on hand. But yeah, the idea is basically that we localize via something that, playing with it a bit, just goes back to the usual definition of a complete Segal space.
Okay. Yeah.
But yeah. So the thing is, we said that we're doing the complete DG model structure. We were defining complete dg-Segal spaces because there was something that should be invertible but isn't. So what is that? Well, it's what I call decay equivalences. So you don't have enough information for now to understand this definition exactly. I just wanted to put it up so that you can see that this looks suspiciously similar to the definition of a quasi-equivalence on DG categories. And that is absolutely on purpose. If this morphism in between dg-Segal spaces comes from a morphism on DG categories, this is basically just the definition of quasi-equivalences on DG categories. So now that I've said that, let me explain what these symbols mean. So, first of all, if we have a dg-Segal space and we have 2 points in the pi 0 of the image of K, we define this fxy to be a functor from cochain complexes to simplicial sets to be like this. If we have a perfect complex, the image by this functor is the fiber of this morphism, where EXY is the DG category with 2 points and E as the morphism between them. And then we said that every cochain complex can be written as a co-limit of perfect complexes. So we will define the image of C to be the co-limit of the images of perfect complexes. We just extend by co-limits. And we call this the DG mapping space of F in X and Y. Now, this definition is scary. It's not super obvious. But don't worry, there is something going on. We can prove that this is always representable. So there always exists a unique Cauchy complex such that fxy is just the map from blank to the Cauchy complex. So I am potentially going to call both of these, use them in mistake one for the other. There's existence and uniqueness. So last thing, we will call the homotopy category of a dg-Segal space a category whose objects are the pi zeros of the image of K, and whose morphisms are the cohomology in degree 0 of the dg mapping spaces, or the complexes assigned to the dg mapping space. We're already doing it. And now we can go back to our definition. So F, a morphism of dg-Segal spaces, is a dk equivalence if the induced morphism on the homotopy categories is essentially surjective. And for every two objects, the induced morphism on the dg mapping spaces is a quasi-equivalence in Cauchy complexes. Now, sadly for us, proving that these are exactly the weak equivalences in the complete dg-Segal model structure has been proven to be harder than we expected it to be. So this is not entirely proven yet. So this is going to be a hypothesis for the rest of this talk. But just assume that this is the case. And now that we have that, let's just do a tiny bit of proving and see how this is actually a model for dg categories. Assuming the hypothesis to be true, let's start with the full faithfulness. So the idea of the proof of the full faithfulness is that it is relatively easy to prove that the functor Sing is fully faithful on free dg categories of finite type. So we're going to try and chop up every dg category into pieces that are free of finite type. And we're going to use that as a way to prove the fully faithfulness for the entire thing. So first of all, we have that the functor on free dg categories of finite type is fully faithful. And then we have that there exists an augmented simplicial object who is composed of free dg categories of finite type, whose homotopy co-limit is equivalent to a dg category. Or to be precise, we had this until less than 48 hours ago when we found an error in the proof. So thank you, Arne. So this is now back to being work in progress. I mean, thank you for real. It's bad to have a proof that is incorrect. So this is now back to being work in progress. We're trying to see how we can solve this. But let's just assume that this works, because we should be able to make it work in some sense. Then, if we have something that is constructed as above, whatever that means right now, then we can see that the homotopy co-limit of the image of this thing is dk equivalent to the image of the original dg category. Yep.
So in this case in particular, by dk equivalence, do you show that it is an equivalence of the complete Segal spaces, or do you show that it is a dk equivalence?
It is a dk equivalence in dg-Segal spaces. This is these are all dg-Segal spaces.
That weak equivalences are dk equivalences. But I mean, you really mean dk equivalence. You show
I show that it is a dk equivalence, okay. Which is actually why we need that hypothesis, because at this point we want this to be a weak equivalence. Yeah. We think this is a weak equivalence.
Okay,
yeah. So we have the homomorphic element of the image is dk equivalent to the object. And then we can see that it's fully faithful by this thing. So we saw that a homomorphic coelement of thing is dk equivalent to the thing of P, assuming the hypothesis that's a weak equivalence. So the image by RE is still a weak equivalence. Now G is a weak equivalence because RE is a left Quillen junction, so it commutes with homomorphic elements. And then we have proven that when the TIs are all free dg categories of finite type, this is fully faithful. So phi is a weak equivalence. So by 2 out of 3, this is a weak equivalence, this is a weak equivalence, then this is a weak equivalence, and we have finished our proof. So we have our fully faithfulness. So let us talk a tiny bit about essential subjectivity. So we're going to try and prove that if we have a dg-Segal space, there always exists a dg category whose image is dk equivalent to our dg-Segal space. So I have shaved quite a few slides on this, so you're going to have to believe me on this. When I say that there exists a simplicial object in dg categories and a morphism from its image to F, such that this thing is a dg-Segal hypercover of F. So I'm not going to tell you what a dg-Segal hypercover is, just it covers F in some way. And so the object that we need, the dg category whose image is dk equivalent to F, is going to be the homotopy colimit of these things. Okay? So again, this is a dk equivalence, which means that if we want this to actually be the essential subjectivity, we need to prove that dk equivalences are weak equivalences. So if we assume the hypothesis to be true, then we have an equivalence of categories between dg categories and complete dg-Segal spaces. And we are good, we have a model for dg categories. Now that we have done this, let's talk about some work in progress. So, first of all, this hypothesis, what do we do with it? Well, in the case of complete Segal spaces, Rezk tackles this by creating a functor, a completion functor, which associates to every Segal space a complete dg-Segal space, which means that he can reduce the problem of proving that every Dwyer-Kann equivalence is a weak equivalence to proving that every Dwyer-Kann equivalence between complete Segal spaces is a weak equivalence. And from that on, it is relatively straightforward. So the big thing here is, how do we define such a completion functor? So Rezk gives this definition. And the problem is that the thing that is going to block in our case is this thing. Because in order to define this, Rezk uses the direct product of simplicial sets. And we can't do that. Because modal structure and monoidal structure are not compatible. So we go back to the original problem, which is that we need to find a monoidal structure in complete dg-Segal spaces that is compatible with our model structure. And the obvious one, which would be the day convolution, does not work because the tensor product of free dg categories is not free. So we can't just say, well, we have functors, so the day convolution will work. So we're still trying to see what this would be. If you have ideas, I will take them.
If all your things are free over graphs, can't you use one from the graph? Like you can take the Cartesian product of graphs and then take associated linear,
But the free version of the
your graphs are already also DG. They're quivers, right?
Yeah, they are quivers.
And what if
So
Wait, how is it simple? It's equal 5.
Also in the DG, yeah, right, because
Yeah,
you
yeah.
go for DG quivers. But I guess it's not surprising that if you want to do a tensor product induced by the tensor product that doesn't really work, which is one DG, and you want to use a day convolution from something as well.
yeah.
But I'm just confused about this warning because for me it's like simplicial sets and chain complexes both are monadal model, and then it's only when you go to simplicial categories and to the G categories that it's not compatible anymore.
Yeah.
So for me, these are like Rezk uses the 9. So why can't you use the
Yeah.
or I mean it's not even the point class product. It's like so Rezk uses direct product of simplicial sets. Why do you need something in G-cat and not in chain complexes?
Yeah.
Because Rezk does not need something in simplicial categories. He needs something in simplicial sets.
Sure. But I don't remember.
It is just heuristic and so like.
Yeah, I mean, it's kind of not the same thing in the sense that Rezk is not working on simplicial categories.
Yeah, so it
he
starts
has
already from a different.
yeah, like he has simplicial objects.
Yeah, yeah.
So it has something that is a lot easier to begin with.
Yeah.
So not the same. So yeah, this is proving to be harder than we expected.
But then what about the pointwise that they were suggesting?
Yeah.
Huh?
What about pointwise?
Pointwise, in what sense?
Not day convolution.
Yeah.
Questions
Just-
again. Sorry.
Oh, yeah. I mean, considering the amount of the people that are still in the room, I think most of you know very well what I'm going to say next, which is I have some work with.
Maybe those.
So I am going to explain our joint work with 2/5 of the audience to the rest of the audience.
And online also.
There's people online, yes, but out of the people online, out of 3 people, Wendy definitely knows because we told her yesterday. But so this is joint work with Arne, Mertens, and Violeta, Borges, Marques. I'm hoping I'm pronouncing that correctly. Good. So the idea is, can we compare complete dg-Segal spaces to other models of DG categories? So we have some results that are hopeful in that direction. So in particular, we have this diagram commutes. So what is this diagram? So we have on top, we have dg categories, complete dg-Segal spaces, and the delinearization to complete Segal spaces. And on the bottom, we have dg categories, completion chain complexes, co-chain complexes, which are their model for dg-Segal categories, and the delinearization to Segal categories. So by saying that this diagram commutes, what we're saying is that the delinearization of the two models coincides, which is not exactly what we want, because if we're doing the linearized version of these things, we would want a comparison without getting out all the stuff that we added. But at least it seems like a good sign. This is probably, it's not doomed from the start. So for now, we are kind of working in this, with this idea. So we have dg-Segal categories on one end and complete dg-Segal spaces on the other end. And we have this zigzag that we think might work, which goes from colex delta k f to co-chain complexes, to colex functors from delta k to simplicial sets. And we could maybe say that this is the same as functors from delta k to simplicial sets. And we expect this to be a good, this to be an equivalence of some kind. So the idea is that free dg categories of finite type might not be the smallest set of generators. We could find something smaller that is actually directed, which is the thing that we need in order to connect with dg-Segal categories. So I don't know how I'm on time, because I think we've been, yeah. So I was going to give a possibility of what this delta k might be, but I think I might just stop here. We've been here for an hour and a half, and I think we all deserve a break. So.